Hey everyone, welcome to my new series 5 Hours 5 on AP Chemistry, where I'll teach you all the content in AP Chemistry in 5 hours so that you can score a 5 on the AP Chem exam. With enough practice problems and watching these videos, and ideally complementing with the class you are taking, you'll be able to certainly score a 5 on the exam. In this video, I'm just going to cover the prerequisites of AP Chemistry, so this is going to be what you typically would cover in a 9th grade or middle school chemistry course, a summary of all that, and then a preview of the AP Chem course itself. So let's get into it. So AP Chem has 9 units, and Unit 1 typically focuses on the initial concepts of moles, periodic trends, photoelectron spectroscopy, and more. Unit 2 typically or mostly focuses on the types of bonds, and Unit 3 is the most important part of the exam since it has the highest AP exam weighting at 18 to 22% of the exam. It typically covers mostly IMFs and some other content like gases, spectroscopy, and solutions. Unit 4 focuses on the types of reactions, and it also covers some intro to like Unit 1 type stuff. So you'll notice later that 4.1 to 4.5, those standards are kind of like Unit 1 in a way. They cover net ionic reactions, or net ionic equations, stoichiometry, and more. Unit 5 is kinetics, which is how fast a reaction goes. Unit 6 focuses on enthalpy, calorimetry, and overall energy understandings, like through diagrams. Unit 7 focuses on equilibrium, so that's the equilibrium constant, the calculations, ice tables, Le Chatelier's principle, and all of that. Unit 8 is acids and bases, which covers buffers, other calculations, and most people think of this as the hardest unit. It's also the second most weighted on the AP exam. And Unit 9 is thermodynamics and electrochemistry, which has content like batteries and lots of calculations, as well as electrolysis. In my opinion, Unit 9 is the hardest. However, most people think Unit 8 is the hardest unit in AP Chemistry. So this is what's typically covered in 9th grade Chem or middle school Chem. You'll see pretty much all of Unit 1 covered, as well as the introductory parts of Unit 2 and Unit 4. One thing to really note here is that units in AP Chemistry don't really make a lot of sense. You'll notice that stoichiometry is 4.5 when in reality, in my opinion, I think it should be covered as early as Unit 1 since it's absolutely essential to pretty much the rest of the course. So I wouldn't really go topic by topic in AP Chemistry, but instead try to develop a holistic understanding of chemistry. So let's get into the actual content. So the first thing to focus on is matter and particles. So just to give some definitions, an atom is the smallest unit of an element. So you might say something like you have one atom of hydrogen, which is H. And then a molecule is going to be two or more atoms covalently bonded. So if you typically see, if you look at hydrogen in the atmosphere, it's going to be H2, which means two hydrogens are covalently bonded to each other. And that means hydrogen gas is a molecule. Then there's also ions, which are charged particles. So one common example is hydroxide, which is OH minus, and you'll notice that that minus means it has a charge of 1 minus. And that is OH itself is a particle, and the charge is 1 minus in that case. An ionic compound is going to be a lattice structure of the ions, and it essentially is held together by attractions between the positively charged cations and the negatively charged anions. So, like it says in the definition here, cations are positively charged ions, and anions are negatively charged ions. So, if you actually look at the diagram here, you can notice that you have Cl minus right here. Oops. You have Cl minus here, which is negatively charged, and then the smaller atoms or smaller ions are Na plus, which are positively charged. As you know, positive and negative charges attract, and that's sort of the simplistic understanding of why ionic solids are held together. And one thing to note is that ionic compounds are not molecules, since in our definition for a molecule, we have that it is covalently bonded, while ionic compounds are not covalently bonded, but they're rather bonded ionically, and we're going to discuss that more later. And then finally, we have mixtures versus compounds. So mixtures are things that are, like it says in the name, an actual mix of all different sorts of molecules and compounds. So one mixture, a common mixture, is air, and that's going to be a mixture of oxygen, nitrogen, and other atmospheric gases like that. While a compound would be an actual substance that's not really separable into multiple distinct compounds, but rather it's its own separate compound like table salt or sodium chloride. So essentially, I think it's pretty self-explanatory that like air or other mixtures are a collection of compounds, and compounds are compounds. Okay, moving on to atomic structure and notation. So one thing to note right off the bat when you're looking at molecules is that charges are going to be indicated in superscript, while the number of atoms is going to be indicated in the subscript. So if we look at the example here, this is a sulfate ion, and you'll notice that there's a sulfur atom, which is indicated by S on the periodic table, and then there's an O, which is oxygen, but you'll see the number 4 in subscript here, which indicates there are 4 oxygen atoms in this sulfate ion. And then in the superscript, you're going to see 2 minus, which indicates that the charge is 2 minus in the case of the sulfate ion. And as for charges, protons have a relative charge of +1, while neutrons are chargeless or neutral, and they have a charge of 0, while electrons have a relative charge of -1. As for isotopes, so isotopes are the same elements with different number of neutrons. So one common example is hydrogen and deuterium. So hydrogen itself has 1 proton and 1 electron, but deuterium has 1 proton, 1 neutron, and 1 electron. So you'll notice they're the same element since they have the same number of protons, but they differ in the number of neutrons. So regular hydrogen and deuterium are isotopes since they have a different number of neutrons, but the same number of protons. And as for how to determine atomic mass, that's going to be taking the average mass of isotopes. So just to clarify that a bit, you can see this calculation here. So we can calculate the average mass of chlorine via taking the mass of its compound, or taking the mass of each of its isotopes and multiplying by the fraction or the percent composition in the atmosphere, right? So in this case, there are 2 common isotopes of chlorine, 35Cl and 37Cl. I'm going to go over what those numbers mean in a bit, but essentially what we do to calculate the average atomic mass of chlorine itself is we take these the masses of these isotopes and we multiply them by their percent composition. So the mass of 37 chlorine is approximately 36.97 grams, while the mass of 35Cl is approximately 34.97 grams. And we multiply by 0.7577 here, since that's the percent composition of 35Cl. And we multiply by 0.2423 for the same reason here. That's the percent composition of 37 chlorine. So just to go over what those numbers actually mean, isotopes will typically be indicated in this AZE format, where A is going to be your mass number, which is the number of protons plus the number of neutrons, while Z is going to be your atomic number, which is the number of protons. And remember that on the periodic table, atomic number is what actually indicates what an element is. So for example, if you have 1 here, that indicates that your element that you're referencing to is going to be hydrogen, no matter what the mass number is here. We know that only hydrogen has 1 proton, so our chemical symbol, which is E, is going to be an H in this case. So for deuterium, we would write 1, 2, H. Since deuterium has 1 proton and 1 neutron, so its mass number would be 2. And of course, it has 1 proton, and the chemical symbol is H for hydrogen. Now, going quickly back to this calculation here, if you're wondering why the atomic mass of 37 chlorine isn't 37, it's simply because of this thing called the mass defect. So that's not relevant to AP chemistry, so I'm not going to discuss it, but just know that that's not a mistake, that's on purpose, and it's the mass defect. So let's continue the atomic structure. So the structure of an atom is essentially there's a nucleus of protons and neutrons. It's this very extremely dense center in the middle of an atom, and you can see it represented here on the in the diagram. So it's a bunch of positively charged protons and neutral neutrons just bunched together, very dense. It's in the center. Now electrons move around this nucleus, and you can see in the diagram this is the Bohr model of the atom, which is actually incorrect, and it's something that is taught very widely in ninth grade chemistry and middle school chemistry, but it's actually incorrect. All you need to know for now, I'm going to go into much more detail about this in future videos, but all you need to know is that electrons are going to move around this nucleus according to probability regions called orbitals. And essentially what that means is that in an orbital, you'll have a higher probability of finding an electron in that position. If you're confused about what that means, don't worry about it. All you need to know for now is what orbitals are and that electrons move around according to those orbitals. You can pretty much discard most of the Bohr model, especially the electron orbiting part, because that's fully incorrect. Now, as for going back to like the isotope stuff, the nucleus is going to be what defines the element and the isotope. So the number of protons is going to define the element, and the number of protons plus neutrons is going to determine the isotope. And as for the electrons, those are going to change for ions because they're going to be what changes the charge of something. If you have more electrons, you're going to have a negatively charged ion, and vice versa. Okay, so moving on to the periodic table essentials. So something I want you all to do, everyone who's watching, is you should open up ptable.org. This is personally what I use for a periodic table when I use one online. And you can use that as a reference as I continue to discuss this. So elements in the periodic table are going to be arranged in order of increasing atomic number or the number of protons. So as you go left to right, you're going to see an increase in the number of protons, and that's going to be indicated on ptable.org. And then you go to the next row and you see another increase, and so on and so forth. It goes in order essentially. And as for the classifications of the elements, you're going to see stuff like non-metals, metalloids, etc. So every element on the periodic table can be categorized as a metal, a non-metal, or the metalloid. There's a bunch of different types of metals like alkali metals, alkali earth metals, transition metals, etc. But the general classifications fall into one of these three categories. And as for the groups of a periodic table, when I say groups, I'm referencing the columns of the table. And those are going to have the same number of electrons in the valence shell. And if you're confused about what that is, that's a very, very important term. It explains a lot of properties in AP chemistry, and I'm going to discuss it a lot more soon. But essentially, a valence shell is the outermost shell of electrons. And these groups in the periodic table typically have similar properties. Now, as for the periods, those are the rows of the periodic table. Those are going to have the same number of energy levels for electrons. Now, again, if you're confused about what that is, I'm going to be discussing that soon, so don't worry. And as you go forward in a period, or a row of the periodic table, the Zeph will get higher as the number of protons increases. So the Zeph is the effective nuclear charge, or the impact that the nucleus has on the atom as a whole. When the number of protons increases, you're going to have a greater positive charge in the nucleus, and that's going to mean a greater effective nuclear charge. That's all that the Zeph term means. Okay, now moving on to periodic table trends. This is a topic that comes up a lot on the AP Chemistry exam, and you probably discussed it significantly in either middle school or ninth grade chemistry. So you can see the trends in the image right here, but I'm also going to explain them. So, you can see it in this image here, and I'm going to go through them one by one. So the ionization energy is the minimum energy required to remove an electron from an atom in gaseous form. So like we mentioned earlier, you have electrons in these different energy levels in an atom surrounding the nucleus, and the ionization energy is essentially the energy required to remove one of these electrons from the atom. Now, electronegativity, on the other hand, is a measure of an atom's ability to attract electrons in a bond. So the reason why this is going to increase across a period or left to right is because atoms are going to more strongly attract electrons due to the increase in Zeph. Like I mentioned earlier, you have an increase in the number of protons, which increases the effective nuclear charge that those positively charged protons have on electrons. And the reason this is going to also decrease down a group or top to bottom is because you're going to see a greater distance between the nucleus and the outermost shell of electrons, or the valence shell of the electrons. So that greater distance is going to decrease the attraction on new electrons. So that's the reason why electronegativity has a trend increasing when you go up and to the right. And going back to ionization energy, it's a very similar explanation. It increases left to right because of the increased Zeph, so it becomes harder to remove an electron, and it decreases down a group, top to bottom, because of the increased distance. So it's going to be easier to remove an electron when you have the greater distance and less attraction. Now, moving on to atomic radius. This is the radius of an atom, which is essentially the half the distance between the nuclei of two identical bonded atoms. So I think atomic radius is pretty self-explanatory in terms of what it actually is, but as for how the trend actually works, you're going to see an increase in atomic radius as you move down a group top to bottom, since you're going to add more and more electron shells, which increases the distance like we've established. So of course that is going to increase the atomic radius. It's also going to decrease down across a period or left to right because of that increasing nuclear charge. So that's going to attract the electrons more strongly, and it's going to slightly pull them in more, which decreases the atomic radius, since the atomic radius includes the electrons. So yeah, when the electrons are pulled in more, the distance is going to be lower. And that's going to decrease the atomic radius. Okay, moving on to electron affinity. That's the energy change that occurs when a neutral gaseous atom gains an electron. So, although it sounds like the opposite of ionization energy, the trend is not exactly the opposite, and in fact, it's the same. And the reason why is because electron affinity increases across a period left to right, because atoms are going to more readily accept electrons to achieve a stable configuration. So what that means is atoms are going to, in like this range, are going to want to take on electrons to shift more here. And the reason why is this column of the periodic table is known as the noble gases. And these have a full octet in terms of their electron configuration. If you don't know what that means, I'm going to explain that soon. Don't worry about it. But what that means is essentially it's very, very stable, this entire column. So, of course, atoms want to be as stable as possible. They're going to want to take on these electrons to achieve that stable configuration in terms of their electrons. So the electron affinity is going to increase since they're going to more readily accept electrons. And as for the groups, it's going to decrease down a group top to bottom because the attraction for additional electrons is going to weaken as the distance increases, like we've established already. And finally, metallic character is just a tendency to lose electrons. Like I mentioned earlier, you're going to see an increase in like this region for atoms that want to gain electrons to shift to this more stable configuration. So the non-metallic character, or the tendency to gain electrons, is going to increase in this direction. And metallic character is the opposite of non-metallic character. So it's going to, of course, decrease or be the opposite trend. And another reason why is if you have something in this range, for example, like one of these uh, elements, they have essentially a, a sole electron in a new energy level. And like I mentioned, I'm going to explain all this very soon. But if it actually loses an electron, it's going to go back to, for example, if we take this element here, it's going to go back all the way to this element here, which is a noble gas. So when it loses an electron, it's going to again get a more stable configuration, which is preferred. So that's the reason why metallic character increases down and to the left. Okay, I've talked a lot about electron configuration so far, so let's actually dive into it. So electrons, as I mentioned, move around the nucleus according to probability regions known as orbitals. So as for what how electrons are actually indicated and the different energy levels I was talking about, there's numbers in front of electron configurations. So you can see that in the periodic table here. Um, these are the electrons in that specific position. So essentially what that means is hydrogen is going to have one 1s1 electron, and then neon, which is this element here, is going to have, or sorry, helium, that's the element there, that's going to have one 1s1 electron, since hydrogen has that, and it's going to have its own 1s2 electron. Then this element here is going to have both of those plus 2s1, and then this has all three of those plus 2s2, and so on and so forth. So as for what these numbers actually mean, I'm going to break that down. The number in the very front indicates the energy level. So you can see here there's going to be 1, 2, 3, 4, 5, 6, 7 energy levels. And those are going to increase as you move down the periodic table. There's some nuance there, but that's essentially the breakdown for now. Then you're going to see a number, and essentially that's a subshell. So you can see here by the way this image is drawn upon, you can see that there's a shell here, which is essentially all of the subshell, encases all of the subshells of that specific energy level. So in the image, if you take the energy level 2, or essentially all of these electrons plus all of these electrons, you're going to see that it has further subshells, and subshells are going to be indicated by the letter. So you can see there's 2s and 2s, and then there's 6 2p's. So the subshells are going to be 2s and 2p. And from there, they're going to be broken down into orbitals. So orbitals are going to be they're going to be inside of every subshell, and S is going to have 1 orbital, P is going to have 3 orbitals, and D is going to have 5 orbitals. So if we look at 2s here, that is going to have 1 orbital. And you can see that here there's 1 orbital indicated in this diagram. And as for 2p, since it's p, it's going to have 3 orbitals, and you can see that here. Don't worry about the different orientations for now, that's not really relevant. And if you had an energy level that had D, for example, 3 has D here, 10D electrons, that's going to have 5 orbitals. And just for future reference, I'm going to discuss this more, but each orbital is going to hold 2 electrons. So as you go across the periodic table, you're going to count 1s1, 1s2, and essentially what that means is that there's 2 1s electrons, since, like I mentioned, every orbital hosts 2 electrons. And the energy level 1 only has s as a subshell. So that's going to be 1s, and then if you move on to 2 as the energy level, you're going to have both 2s and 2p. So you're going to have 2s electrons indicated by 2s1 and 2s2. And then you're going to have 6 2p electrons indicated by 2p1 through 2p6. And again, 2p, there's 3 orbitals of that. Each of those hosts 2 electrons here. You can see that here. So that's going to be 6 total electrons. And as for the energy level 3, this is where we also add the D subshell. So you're going to have 3s, 3s electrons, 6 3p electrons, and then you're going to have 10 3d electrons. Now, if you're wondering why 3d doesn't start here instead of just skipping these two elements seemingly, that's a whole bunch of other nuance that I'm going to go over in future videos. But essentially, I'm sure you see mostly the pattern in this periodic table by the way these electrons are written out, right? So just to quickly go over how you would write the electron configuration of something, if you take, for example, let's take this element here, neon, how you would write this is you would indicate all of the electrons that neon has, which is all of the electrons of the elements before it and the electron that it has itself. So in this case, it would be 1s1, 1s2, 2s1, and so on and so forth, and you would list them all going in this order, then this order, until you reach the element itself. Then you list that element, and then you're done. So you would go on until you list 2p6, and that would be your electron configuration. So I know that was a very dense slide and there was a lot of information on it. I hope you understood the general patterns, and essentially that there's a shell, which is an energy level. Inside there are subshells, which are indicated by letters, and inside there are orbitals, and you can see the number of orbitals per subshell according to what's written here. Of course, we're going to discuss electron configuration more. There's a lot of content in it, and it's pretty essential for the rest of the course. So, like I mentioned earlier, you can write the electron configuration of an element by taking the electrons of all the elements before it and then including that electron itself, which you can see here for neon, which is this element here. However, there's a thing you can do called a noble gas configuration. And what that means is you essentially take the electron configuration of the last noble gas. Remember, that is this column right here. So you're going to take the electron configuration of that column right there, whatever the last noble gas was, and then you're going to list the electrons from there only. So if we go back to this example here, if we take, for example, this element here, which if you look at it is going to be strontium, if you look at ptable.org. So if we were to write the noble gas configuration of strontium, we would just look at the last noble gas. So if we go in this direction, we look here, this is not a noble gas yet. So then we go back to here, and this is a noble gas, namely it is krypton. So we simply put the chemical symbol of krypton in brackets, and then we list the electrons after it, which are going to be 5s1 and 5s2. And that is going to be the noble gas electron configuration of strontium. And you'll notice it would be a lot quicker to write this configuration instead of fully writing out every single electron here, which would actually cause you to write out 38 individual electrons. Instead, here we're just writing one noble gas and then 2 electrons. Okay, now you'll also see charge patterns. So 1a, which essentially means this column here, excluding hydrogen. Hydrogen is an exception to most trends. Excluding this hydrogen here, this entire column is going to have a charge of 1+ when it's forming ionic bonds and ionic compounds. And the reason why is because it really wants to form this noble gas configuration of this column here. So if it loses an electron, it's going to go back and achieve the electron configuration of a noble gas, which is very stable. That's the same reason why you're going to see a charge of +2 in this column, because if you lose two electrons here, you're also going to go back to the very stable noble gas configuration. And the same thing applies to 7a, which is this column here. If it gains an electron, it's going to turn into the electron configuration of a noble gas, which is very stable. So you're going to see those charge patterns very frequently, and there's very few exceptions to those. So yeah. Now, there are 3 rules as to what electrons actually fill. And those rules are the Aufbau principle, the Hund's rule, and the Pauli exclusion principle. So let me go through those one by one. The Aufbau principle simply states that electrons fill orbitals in increasing energy order. So I'm going to be discussing electron configuration more deeply in another video, since there's still a lot of content left to cover. But you can see here that the y-axis in this case is energy, and it's going upwards. So you see the 1s orbital has the lowest energy, the 2s has the second lowest, then 2p, then 3s, then 3p, then 3d, and so on and so forth. So you're going to, 4s is actually lower in energy than 3d, but essentially you're going to see that the electrons fill the orbitals in increasing energy order. If you go back to this pattern here, you'll see how 1s fills up, then 2s, then 2p, then 3s, then 3p, then actually 4s. So it's not just by number and then by letter, but instead by energy level. And although it's kind of unclear in this diagram, 4s is actually lower in energy than 3d. So that is going to be the Aufbau principle. And then as for the Hund's rule, so the Hund's rule essentially is that the electrons are going to singly occupy all the orbitals, and then it's going to double up. So like I mentioned earlier, you're going to have 2 electrons per orbital. So if you have a 1s orbital, like it shows in the diagram, that's going to be able to store 2 electrons. However, if we take the example of 2p, we actually have 3 2p orbitals. So if we label them here, each as 2p, and as we go to fill these electrons, they're not actually going to fill like 2 here and then go on and fill the rest, but instead they would actually fill 1 here, then fill 1 here, then fill 1 here, and then they would start to double up in the same orbital. So that's just something to keep track of in the future when you're going to be writing these types of electron diagrams. And then there's the Pauli exclusion principle. So the Pauli exclusion principle essentially is going to is saying that the electrons in the same orbital are going to have opposite spin. So you'll notice how I wrote 1 down arrow and 1 up arrow for electrons. In case you're wondering what those arrows actually mean, they're just a way to signify electrons. The down arrow essentially means that there's a down spin, while the up arrow means that there's an up spin. And in the same orbital, for example, if we take 1 2p orbital, you're going to see always 1 down spin, 1 up spin. It doesn't matter the order that you write it in, but they're always going to have opposite spin, and it would be incorrect to write a 2p orbital with 2 electrons that both have up spin. This would be incorrect, and you would score poorly on the AP exam. So, just to summarize, rule 1 in the diagram here is fill orbitals by energy, which is the Aufbau principle. Rule 2 is up to 2 electrons per orbital, which is the Hund's rule. It's just another rule showcasing what I said earlier about 2 electrons per orbital. And it's also a combination of the Pauli exclusion principle, and rather 3 here is correlating to Hund's rule, so in case the diagram is helpful. Okay, moving on to photoelectron spectroscopy. So photoelectron spectroscopy is a way to measure the relative energies of electrons in molecules or atoms. So if we take the atom of phosphorus, like the diagram showcases, we essentially measure the binding energy, which is the x-axis here. Don't worry about the unit, but essentially we measure the binding energy of specific electrons in that atom or molecule and plot it. So you'll notice that instead of increasing as you go right on the x-axis, it actually decreases. And the reason why is if you have a nucleus here, right? We'll just label it N, and then you have this is like what you would draw for the Bohr model. You would have like an electron here, 1s, two 1s electrons, and then you have 2s electrons. You can see the dots there. Essentially, the 1s electrons are going to be closer to your nucleus, and since that distance is lower, that's going to have a greater binding energy. Since the binding energy is the energy required to remove those electrons. So since they're bound very, very closely to the positively charged nucleus, while the electrons are negatively charged, it's going to take a lot of energy to remove one. So the x-axis is written in this way, in decreasing energy order, because the electrons here are going to be the 1s electrons, and then you're going to see 2s electrons here, and 2p, etc. So it's going in order of the increasing distance from the nucleus, where a greater binding energy means it's going to be closer to the nucleus. So you'll notice we can essentially already kind of get a sense for how to read this, right? We can just start to label each of these electron peaks. So one thing to notice is that you also have this y-axis here. You might not have this on all photoelectron spectroscopy spectra, but it showcases the relative number of electrons. So you can see that these two peaks are the same. And the reason why that is because this peak is both of the 1s electrons, while this is both of the 2s electrons. And you'll see this peak is 3 times greater, and that's because this is all 6 of the 2p electrons. Another thing to note is that even though there are two 1s electrons, you're not going to see two different peaks, since they're going to have the same distance from the nucleus, so they're going to have the same binding energy. So you could start to read a photoelectron spectra by just going in order of the periodic table, reading 1s, then 2s, then 2p, then 3s, and then you'll notice that this doesn't have all 6 of the 3p electrons. Otherwise, it would be the same height as a 2p peak. So instead, since it's about half of this, or if this helps, 3/2 of this peak, so 3/2 of that peak, half of the 2p peak, we know that this is going to be 3p electrons. Then if you go back to ptable.org, you're going to see, or ptable.com, you're going to see that this correlates to phosphorus, of course, because you have 3p electrons. So that sort of just gives you a sense of how to read it. You just go in order of the x-axis, and you go in order of the periodic table. You look at the height of the peaks, and you see what matches up. When you start to see something that doesn't match up, you count the number of electrons in that valence shell, the outermost shell, and then you're going to correlate that to whatever element it is on the periodic table. So let's do some practice here. This is from an AP Chem FRQ. Pause the video now if you want to solve this yourself. Okay, so the answer for what element this is calcium. And the reason why, don't worry about these units again. They're just telling you the binding energy. The actual numbers don't matter for this problem. But as you can see, you can verify that they're in decreasing order, the binding energy. So you know this is going to be the 1s, or the two 1s electrons. This is going to be the two 2s electrons, and we see this peak is 3 times longer. That's going to be the 6 2p electrons. We're still doing good so far. We haven't really run out of electrons. These are going to be the two 3s electrons. These are going to be the 6 3p electrons. And then we see we're expecting these to be the two 4s electrons, which they are, and then we don't see another peak for 4p. So using our electron configuration and knowing that the last electron here is a 4s2 electron, looking at ptable.com, we see that this matches up with calcium since it's in the same position that the 4s2 electron is in. So our answer is calcium. Okay, now we're going to cover the types of bonds. So there's three main types of bonds you need to worry about here. There's an ionic bond, a metallic bond, and then there's covalent bonds. So one really key understanding I want you to get from this video is that ionic and covalent bonds are simply a spectrum. And that spectrum is all dependent on the electronegativity difference, which you can see here. This on the x-axis is the electronegativity difference on the Pauling scale. You don't need to worry about what that is for now, but you'll see that if the electronegativity difference is great between two atoms, that's going to be an ionic bond. If it's very small, it's going to be a non-polar covalent bond. I'll explain what that means later. And then if it's somewhere in between, it's going to be a polar covalent bond. So really nothing is purely ionic or purely covalent. Well, actually there are some bonds that are purely covalent. I'll explain those later. But yeah, you'll see that it's all a spectrum. And as the electronegativity difference between the two atoms that you're binding increases, it's going to shift more towards ionic bonds. As they decrease, they're going to be non-polar covalent bonds. And the cutoff is if it's 2 or greater on the Pauling scale, that's going to be an ionic bond. If it's less than 0.4, it's going to be a non-polar covalent bond. And if it's in between, it's going to be a polar covalent bond. So, essentially what that means is, let's have an example here. If we take something like O and H, right? If we have these two binded together, an oxygen atom and a hydrogen atom, this by itself is not a stable molecule. It's an ion, not a molecule, but you'll notice that if you look at the electronegativity trends, O is pretty up and to the right. So it's pretty polar, it has a pretty high electronegativity, whereas hydrogen doesn't actually have that. So the difference between these is pretty significant, and that's going to be a polar covalent bond, not an ionic bond, and I'll explain why. An ionic bond is typically going to be a metal plus a nonmetal, since those are going to have pretty high electronegativity differences, considering one really wants to lose an electron and one really wants to gain an electron to both achieve that noble gas configuration. So if we take a classic example like NaCl, this is Na binded to Cl, and Na really wants to lose an electron. It really wants to have a positive charge, because if it loses an electron, it achieves the noble gas configuration of neon. So it wants to lose that electron. And chlorine wants to gain an electron, because if it gains an electron, it'll achieve the noble gas configuration of argon. You can look at the periodic table to verify this. So it wants to have a negative charge, essentially. So this works out because one of the atoms wants an electron, one of the atoms wants to lose an electron. So they essentially trade electrons. The sodium is going to give an electron to the chlorine, or the cation is going to give an electron to the anion. And that's why table salt NaCl is an ionic bond. Okay, and as for covalent bonds, you can see this here. This is not a metal plus a nonmetal, so it's typically not going to be ionic, and in this case it isn't, but since the electronegativity difference is pretty significant, it's going to be a polar covalent bond. And what that means is that one atom in that bond is going to tug on electrons more than the other atom. So in this case, oxygen wants that electron more than hydrogen does. So it's going to, if we have like electrons here, I'll just label them with these minus signs here, you're going to see more on this side of the bond since oxygen wants it more than hydrogen. And you can indicate that via this, wow, I suck at drawing. You're going to indicate that via this symbol here, which means essentially a temporary negative charge, or a dipole moment is what you would call it. You don't need to worry about what that means for now, though. And you would indicate the same thing on this side this has a slight positive charge, since it doesn't want the electrons as much as oxygen does. Now, as for nonpolar covalent bonds, that's going to be where the electronegativity difference is pretty small. So some examples here are going to be CH. This is a nonpolar bond. Both of these essentially want electrons the same amount. There's a very, very slight electronegativity difference, but essentially they're fully covalent. And if you want a true fully covalent thing, just look at two identical atoms bonded together, like hydrogen gas H2. That's going to have two hydrogen atoms bonded to each other. And in this case, since they're the exact same atom, they're going to have the exact same electronegativity, and they're going to want the electrons the exact same. So they're 100% covalent, essentially. Okay, so now that you understand what ionic bonds are, which are sharing electrons, or sorry, not sharing electrons, one atom gives an electron to another atom, and covalent bonds, which is sharing electrons, I can move on to metallic bonds. So metallic bonds are where you have a positively charged, a bunch of positively charged metal atoms, and they're going to be in a sea of electrons. So how that essentially works is if you take something like, for example, copper, right? You have a bunch of copper atoms here. I'm just going to draw 3 just to save some time. But yeah, you have a bunch of copper atoms here. You're going to have a bunch of electrons surrounding it. I'm indicating this with minus signs. So these electrons are kind of like a sea, right? They're just randomly about, and each of these positively charged metal atoms is going to attract this sea of electrons, and that's what holds the metal together, essentially. So metallic bonds are typically not that important for AP chemistry, but it's something you should still know. And a pattern you should definitely know is that when you have two metals, they're going to form a metallic bond. When you have a nonmetal and a nonmetal, they're going to form a covalent bond. And when you have a metal and a nonmetal, they're going to form an ionic bond. When you just have two atoms in a bond, that's essentially the pattern that you've got to know, and that's what most binding patterns are going to follow. Okay, moving on to stoichiometry. This is technically in Unit 4, but like I said, I think it really should be covered in Unit 1, since it's really essential to the rest of the course. So what stoichiometry is essentially math for a chemical reaction. A chemical reaction is going to indicate what species on the left side of the reaction form the species on the right. So you can see in this example here, you have 2 moles of hydrochloric acid, this right here, reacting with 2 moles of sodium to form 2 moles of sodium chloride, table salt here, and 1 mole, it's not labeled, but this essentially means 1 if there's no coefficient, 1 mole of hydrogen gas. So that's how you would verbally describe a reaction. And each side in a chemical reaction should have the same number of each type of atom. So you can see here, there's 2 Na. And on the right side, you can sort of like treat this like parentheses. There's also 2 Na. This 2 is going to apply to both the Na and the Cl. So there's also 2 Na here. Same thing applies here. There's 2 H's if you treat this like parentheses. And same thing here, like I mentioned, the subscript indicates there's 2 hydrogen atoms. So that's good. That balances out. And then the same thing here, there's 2 chlorines here and 2 chlorines here. So overall, this is what we would call a balanced reaction, since it has the same number of each atom. So when I was describing this verbally, I said this word called moles. And moles are very important for math and chemistry. A mole is 6.022 times 10 to the 23 atoms, or molecules, or whatever it is you're referencing. So you can technically really have like a mole of cars, and that would be 6.022 times 10 to the 23 cars. But of course, you typically use it in a chemistry context, where a mole of carbon, for example, would be 6.022 times 10 to the 23 carbon atoms. If you were referencing water molecules, a mole of water molecules would be 6.022 times 10 to the 23 water molecules. So I hope you understand that value. And if that seems a bit random. There's a whole bunch of history behind it, but you don't need to know it for AP chemistry. Now, something that's very important is that you measure this thing called molar mass via the moles. So you'll see on ptable.com, if you look at the number below the word of the chemical element, so if you look at like boron, for example, you see B, then below it boron, and then below it 10.81. And what that means is that 1 mole of boron atoms has 10.81 grams. So you're going to see a lot of conversion between moles and mass using molar mass there. So if I had half a mole of boron, I would just multiply 0.5. Let me actually do this calculation here. If I had 0.5 moles of boron, I would reference the molar mass of boron on the periodic table to see that there's 10.81 grams of boron per mole of boron. So if you did this math here, you would end up with approximately 5.4 grams of boron. And you can also do the calculation vice versa. If you had 5.4 grams of boron, you could calculate that out to be 0.5 moles of boron. So moles are going to be what you are going to use in stoichiometry. Like for example, if we had 2 moles of hydrochloric acid, that's going to form 2 moles of 2 moles of sodium chloride here. So what you can do is if you have a certain mass of hydrochloric acid, you can convert it to moles and then use the ratio between the moles to then find the number of moles of the product you'd be calculating, which is sodium chloride in this case, and then convert to the number of grams of sodium chloride. So you can see a worked example here. You're going to want to okay, let's say we have this unbalanced reaction here. This would be the balanced reaction, and I'll show you how to balance a reaction later. But essentially, if we have 36.04 grams of water, how many grams of O2 are we going to form? That's just the question we're going to work through here. So the first step would be calculating the molar mass of water. So water is H2O. And although you have the molar masses of hydrogen and oxygen alone, on the periodic table itself, you don't have the molar mass of water. So you're actually going to want to calculate that by using the number of atoms you have in this molecule. So you would have 2 hydrogen atoms, and you know the molar mass of hydrogen is 1.01 grams per mole. So you would multiply that by 2 since you have 2 of those atoms. And then you have this oxygen atom here, which has a molar mass of 16 grams per mole. So you would add these two to get the molar mass of water being 18.02 grams per mole. And you'd use that in this calculation here. So if you want to look at this previous slide and understand like how to solve it, like I kind of did here, and try to solve it on your own using what I described, pause the video right now. Okay. I'm going to work through this solution. So we have 36.04 grams of water. And we know that there's 1 mole of water, H2O, per 18.02 grams of water. So we have 2 moles of water. You can kind of tell already because it divides evenly. But we know that we have 1 mole of O2 per 2 moles of H2O. And if you're wondering why that is, that's where we look at the balanced reaction and we look at the coefficients here. So In the balanced reaction, you'll notice this 2 in front of the water, and you'll notice this invisible 1 in front of the oxygen, O2. So that's essentially what stoichiometry is. You're finding the relationship between the reactants and the products. And in this case, per 2 moles of water, you're going to have 1 mole of oxygen gas, O2. So that's the conversion we use here, since we eventually do want to find the grams of O2. Then we find the molar mass of O2, so that's just going to be 2 times 16, since 16 is the molar mass of oxygen, and we have 2 oxygen atoms in O2. That means that we're going to have 32 grams of O2 per mole of O2. So all in all, if you calculate that, that's going to come out to 32 grams of O2. So that would be our answer to the question. Okay, let's go over how to actually balance these reactions. On the last side, I just balanced it for you, but in this side, we're going to cover how to actually balance one of these. So you can see this unbalanced reaction here. I've put in blank slots for the coefficients, so you can fill those in. If you want to give this a shot and try to balance it, remember balancing means that you have the same number of each type of atom on each side, the left and the right. Go ahead and pause the video now and try to solve it yourself. Otherwise, I'm going to show you a structured way of how to start to balance reactions. Okay, so this might seem overwhelming at first to try to balance. One thing that I really like to do is kind of form a table here. So I just use R for reactants on the left-hand side and then P for products. And then you're going to have each of the individual types of atoms or elements here. So you have AU, and then you have S, these two here, and then you have H. So those are the only 3 we're dealing with right now. So we're going to form this table here, and we're going to write the number of each type of atom on the left and the right here. So right now, with the unbalanced reaction, we have 2 AU atoms, and then we have 1 AU atom here. For sulfur, we have 3 on the left, right here, and then we have 1 on the right. Sorry. We have 1 right here. And then for hydrogen, we have 2 on the left, and then also 2 on the right. So from here, you'll notice that our end goal, sorry, I'll rewrite this for clarity. Our end goal is for each of the R and P columns for each of these types of atoms to be the exact same at the end of our balancing. So something I really like to do is you take one that's off or not even on both sides. So let's take AU for example. And you look for something that has an individual atom in it. So essentially just that element in its in that species. So on the right hand side here we have AU, and that's only AU. So whatever coefficient we put in front of this, it's only going to impact AU. So if we put like 7, for example, that means there's going to be 7 AU atoms. And it's not going to affect the number of sulfur atoms or hydrogen atoms at all. Let me just scribble over this for now. But yeah, you'll notice it's a very powerful tool because it allows us to balance these a lot quicker. So something we can do right off the bat is, oh, we only have 1 on the product side. So let's just make this coefficient 2. And now we can cross this off. Now our AUs are balanced. So we only really have to deal with our S's now. And you'll notice on the product side there's only 3 S's. Since there's 1 S in this molecule, and that's the only molecule with sulfur, let's just multiply this by 3. And then we end up getting 3 on both sides. You have 3 sulfur here and 3 sulfur there. But you'll notice that this molecule, H2S, also has hydrogen in it. So you just change the number of hydrogen atoms on this side, 3 times H2. So you actually have 6 hydrogen atoms on this side now. But thankfully, we can easily balance that because hydrogen is alone on the reactant side here. So just to balance that, we need 6 hydrogen atoms on the left, so we just put a coefficient of 3 in front of this H2. So our final answer would be AU2 2s3 plus 3h2 reacts to form 2Au, excuse my handwriting, plus 3H2S. Okay, now we're going to have you try a full problem by yourself. And you're going to balance the reaction and then do this calculation, and I'll showcase the answers at the end. Pause the video now to try it yourself. Okay, this is the answer. If you tried to balance this reaction, you'll notice that you essentially want to start with this oxygen first, since you have oxygen O2 isolated on the reactant side here, and then you're gonna want to go about the other species and try to balance from there. Yeah, that's the balance reaction. And then this is the number of moles of water you'll have. I'm not going to go into the specific calculations, but I'll just like lay out the pathway here, and then you can actually do the calculations yourself if you're stumped by this problem. But we have grams of ammonia, so we're going to want to convert this to moles of ammonia. And then we use our coefficient here. So we have 7 moles of O2, we're looking at water here, moles of water. We have 6 moles of water here per 4 moles of NH3 ammonia here. So then you convert using that ratio to the number of moles of H2O that you have. And then using the molar mass of H2O, you convert that to grams of H2O. You don't need that for this problem since it asks for moles of H2O, but if you wanted to, you could easily calculate the number of grams by just multiplying the molar mass of water by 0.75, since you know you have 0.75 moles. Okay, we're nearing the end now. We have net ionic equations next. So net ionic equations are essentially they're equations that remove spectator ions, or ions that don't participate in the reaction. So let me contextualize this first. One thing to notice is that you'll often see these things in parentheses next to a substance. And that's going to be the phase of that substance. So if you see a G, that means that substance is in its gaseous form. If it's L, that means it's liquid. If it's S, that means it's solid. If it's AQ, that means it's aqueous. And that means it's dissolved in water and it's split up into its individual ions, its cations and anions. So the balance reaction is typically what we've been used to working with. And it actually groups these aqueous species together. In reality, these are already split up into Ag plus and NO3 minus. But we write them as aqueous because that's just more convenient in some regards. So the complete ionic equation would be splitting up each of these aqueous substances into its individual ions and then writing that full reaction here. So you'll notice that this AgNO3 splits up into Ag plus and NO3 minus, like I said, but if we take something like solid AgCl, that stays as it is because it's not aqueous, so it's not going to split up into individual ions. And as for the net ionic equation, it's going to remove spectator ions, which are ions that don't actively participate in the reaction. And a way to figure this out is if you have the same reaction, or the same ion on each side of the reaction, that ion is not actually participating in the reaction. So it's something you'll notice here. Na plus aqueous is on this side. And it's also on this side. It's unchanged. The coefficient is the same. It's 1. So these are Na plus is a spectator ion. So you can cross that off if you're writing the net ionic equation. Same thing applies for NO3 minus. It's on both sides. So our net ionic equation would be that with everything that's a spectator ion removed. So it would be this. So it's important to note if you're asked for the molecular equation or balance equation or complete ionic equation or net ionic equation when you're determining what to write on the AP chemistry exam. Okay, last but not least, this is an important but pretty obvious distinction to make. There's physical and chemical changes. So physical change is when matter changes form, but actually not the identity. So that's going to be when something changes phases or it just splits or becomes bigger or something, but the chemical formula stays the same. So you'll notice um, in this example here, right, if we have um, something melting, let's just say this is water for simplicity, right? If we have water melting, that essentially means that water is going from its solid form to its liquid form. So that's a physical change. It's changing phases from solid to liquid, but it's not changing what it is exactly. So it's not becoming some new substance. Same thing applies for other physical changes like shredding a piece of paper or chopping up some wood. Boiling, again, would be changing something from the liquid phase to the gaseous phase. So essentially, any physical change that doesn't change the chemical formula is going to be a physical change. But a chemical change is going to actually form something new. So whenever a chemical reaction happens, that's going to be a chemical change. In the case of rusting, for example, that's going to form iron oxide or something else on this nail here, and it's going to that's essentially a new chemical reaction with new products. So that's a chemical change on the surface of this nail, while these examples are not changing chemical identity, so they're physical changes. And I hope that's clear enough. And that's the end of the prerequisites for AP Chemistry. Again, I'm not including this in the total time for the 5 hours, since this is sort of something you should know from middle school or ninth grade chemistry. And apologies if this video was a bit long, but I hope you understood everything from what I've explained. If you have any questions, leave them in the comments or email me, and I'll be sure to respond. Thank you for watching.